So today is a third class of chemical bonding and the molecular structure for class 11. So in this class, we will discuss about the bond enthalpy and the bond order. So first, we will discuss about the lattice energy. What is the lattice energy? Lattice enthalpy. Lattice enthalpy, that is, it is a required energy to completely separate completely separate 1 mole of solid. 1 mole of solid, this is the very important term, the 1 mole of solid to gaseous constituent. So what is the mean of this line? So lattice enthalpy is means that it is a some amount of energy, that is a some amount of the energy which is the needed to completely separate 1 mole of the solid to its corresponding gaseous constituent. Suppose, for example, to discuss the definitions of this lattice enthalpy, suppose I am taking here an example, this is a NaCl. Okay, so NaCl here, it is a solid. So to dissociate it, to separate it, sodium ion and the Cl minus ion, this is the 1 mole. Suppose this is the 1 mole NaCl solid. So this 1 mole NaCl solid, now I am going to separate as a sodium gas plus and the Cl minus gas. So here what is happening? NaCl is a solid, but we are separating these corresponding cations and these corresponding anions, these corresponding cations and corresponding anions in a gaseous state. So to separate, how much energy is needed? How much energy is needed? That is called actually, that is called lattice enthalpy. Now question is, why it is coming the lattice? If you see the lattice of the NaCl, this lattice is uh, completely packed. What is meant by the completely packed? That means there are the attractive force. There is the attractive force between Na plus and the Cl minus ion. This corresponding to opposite ion is there. Na plus and the Cl minus ion. So between this opposite cations and these anions, there is a attractive force. Another force is there. This is a repulsive force. Okay, so repulsive force is there. Cations, Na plus ion, or it could be Cl minus ion and the Cl minus ion. So there is a two force. One is the attractive force, another is the repulsive force. Attractive force between this opposite ions and the repulsive force between the same ion. Okay, so due to presence of this attractive force and the repulsive force, NaCl solid is the very compact. If you see the lattice of the NaCl is completely packed. So to define these two force, attractive force and the repulsive force, and to define, so we need this some amount of the energy to break this Na plus ion and the NaCl solid to its corresponding cations and the anions in the gaseous state. So that's why we need this some amount of the energy to break the NaCl solid, because there is a attractive force and there is a repulsive force between the ion. That's why so because so presence of this force initial is the very solid. So this is the lattice enthalpy. So every lattice, if you see the KCl for that initial, for the KCl, if you also see the water for this water molecules, every lattice will have the some amount of the lattice enthalpy, because suppose we need the some amount of this energy to break the corresponding to break the solids state to the corresponding cations and the anion in a gaseous state. So for that initial case, we need the amount The lattice enthalpy is kilojoule per mole. Uh, per mole initial solid, to break the initial solid per mole, we need 788 kilojoule energy. That is called the lattice enthalpy. That is called the lattice enthalpy. Now, there is another point. We will know about some bond parameters. So, first bond parameter is that bond length. This is a very important thing. Okay, so let us consider this is the A atom and this is the B atom. A atom and B atom, they are connected by a bond and they are forming AB molecule. Okay, so only two atoms is there. Between A and the B there is a bond. Now question is that what is the bond? What is the bond length? So this length is called the bond length. This length is called the bond length. No. Always remember that between the two atoms, this bond is always vibrating. Always vibrating. Uh, Vibration is there. Always there is a vibrations between the A and the B atoms. Okay. So this bond length, so due to the presence of that vibration between the A and the B, the bond length is not fixed because it is the vibrated like a spring. Okay, that's why the bond length is not the fixed. So whenever sometimes you can see that bond length is greater, sometimes it is the bond length is lower because presence of the vibration. So that's why there will be a definition of the bond length is that bond length is defined as the equilibrium distance between the two nuclei of two bonded atoms. So whatever nuclei is present here, the A molecules and for that the B molecules. So between this A and the B nuclei, this distance, this equilibrium distance, this term is very important. This equilibrium distance. Okay, this equilibrium distance is called bond length. So we cannot say this fixed distance because there is a vibrations. There is a vibrations between these two atoms. Always vibration is present. So always it is the vibrating. So bond length will be decreasing and the increasing, decreasing and the increasing. That's why we need a term. This is called the equilibrium distance. Now there is two terms. One is called covalent radius. What is called the covalent radius? First of all, we know that what is the covalent bond? Covalent bond means this bond where the bonding pair is sharing by the two atoms. Okay, suppose A and the B is there, so this is a covalent bond. That means this bonded electrons is sharing by B and also equally is sharing by the A. That is called the covalent bond. Now, what is the covalent radius? The covalent radius is that the radius of nuclei, core nuclei. What is the mean of that line? The covalent radius is measured approximately as the radius of an atom's core, which in contact with the core of another atoms. Okay, suppose there is two atom is there. This is the A atom and this is the B atom, and this is the valence shell. This is the valence shell. This is the valence shell, and it is the nucleus. The inside circle is the nucleus. So covalent radius is mean that whatever distance is there. So this is the covalent bond. So this distance is called covalent bond. Now what is the radius? So this is the radius of the R of A and this is the R of B. So covalent. So to define the covalent radius, you have to know. You have to first of all sure that these two nuclei are the bonded. Covalent covalent radius is coming from the covalent bond. But if you see, this is not a covalent bond. Okay, because this this nuclei is not, this nuclei and this nuclei is not the bonded. There is a gap. Okay, so this is a very important point. That's why I have written wrong. Okay, so covalent radius. When if you define the covalent radius, then you have to first draw the covalent bond. So to draw the covalent bond, you must know this nuclei, this core of these two atoms will be attached to each other, and they will form a bond that is called the covalent bond. This is a atom, this is a B atom. So A atoms, this is the core, and this is the core of the B atoms. So this is a total. So this is the R is the covalent bond. The covalent bond length is the R, and this is the RB, and this is the R of A. R of A and the R of B are covalent radius of A and B atoms respectively. Okay, so this is the core of the A and this is the core of the B. They are the attached by the core. So this is called, so R is equal to RA plus RB. Okay, so this is called the bond length, and this R of A and the RB are the covalent radius of the corresponding atom A and the B. So this is the covalent radius. Now, van der Waals radius. Van der Waals radius is that is it represents the overall size of the atom, which includes its valence shell in a non-bonded situation. So they are not bonded. Van der Waals radius, it is called, they are not bonded actually. Okay, how it is that? So this is the line, is non-bonded situation. So they are not bonded. So this is called non-bonded. So if you draw, now I will draw that. Okay, so this is the core, this is the nucleus, but this is the valence shell. So this valence shell of the A atom, this valence shell of the B atoms. So this is the valence shell of the A atom, this is the valence shell of the B atoms. These are the attached to each other, but this nuclei, it's not attached. That's why it is called non-bonded situation. So it is a non-bonded situation where these two nuclei are not attached. In that situation, this length, and this length. So this is a RA and this is the RB. Okay, so this is a RA and this is the RB. So this is called van der Waals radius for that RA and the RB. So here RA and the RB are van der Waals radius. This is an important term. This is a non-bonded situation. So when they are not the bonded, when the two nuclei are not the attached to each other, is not the connected, is not the connected to each other. Only the valence shells are the touched with is another valence shell of the another atoms. Okay, then we can say it is a non-bonded situations, and whatever radius will be there, that is called the van der Waals radius. Actually, when these atoms the A and the B, when these atoms A and the B are the similar atoms, then the van der Waals radius, will be the half of the bond length. Okay, the half of the bond length. So suppose here the bond length is the R. So van der Waals radius will be R by 2, because the two atoms are the similar now. So when the two atoms are the similar, then RA equal to the RB. Okay, so the RA by RA plus RB equal to the 2R. So the van der Waals radius will be 2R by 2 equal to the R. So when these two atoms are the similar, like the F2Cl2O2 N2H2, here the two atoms are the similar. But when they are the not will be the similar atom, then there will be have the specific van der Waals radius of the specific atoms. So for that the covalent radius, so again for that the covalent radius, just remember the core of atom, and for that the van der Waals radius, just valence shell of atoms. Van der Waals is V and valence is A. In this way you have to the remember for that van der Waals radius, this valence shells, and for that covalent radius, this C and the C, so 4. Okay, so this is the point. Another is the bond angle. Another parameter is the bond angle. Now what is the bond angle? Bond angle is defined as the angle between the orbitals containing bonding electron pairs around the central atom. What is mean? Just remember that it is defined as the angle between two orbitals which are the containing bonding electrons pair. Suppose if you see the O2, the bond angle is 104.5 degree. Now what is mean that this line is containing bonding electrons pair orbitals. So here if you see the oxygen's electronic configuration 1s2, 2s2, 2p4, 2p4, and if you see this hydrogen, this is the 1s1. So in this water, when this water molecule is forming, then 2p and this 1s, these two orbitals are involved in this forming this covalent this bond. Okay, so if I draw, so this is the lone pair and this is the 2p orbitals, this is the 1s and this is the 1s. So these orbitals has the 2 bonded electrons. So this is saying that it is defined as the angles between the two orbitals. So this is a one orbital, this is the one orbital. So between these two orbital, whatever angle is there, that is called bond angle. That is called the bond angle. That's it. There is another, nothing is there. Now, what is the point? So there is something is that around this bond angle, so from that value, we can know about the shape of molecule. Okay, just remember that from that bond angle value also we can know the shape of the molecules. Now the bond enthalpy. Now what is mean by the bond enthalpy? So it is defined as the amount of the energy they required. So it is defined as the amount of energy required to break 1 mole of bonds of a particular type between two atoms in a gaseous state. So there is this some point. First point is that it will be the gaseous state. Okay. So why it is saying that gaseous state? Because suppose water. So to break this bond, this OH bond, to break this OH bond, you have to first boil. You have to first this boiled water. So once if you boil this water, then this water will go the liquid state to the gaseous state. Okay. So in this gaseous state, actually this OH bond will be. That's why they are saying in gaseous state. So bond enthalpy is nothing. It also a some amount of energy which is required 1 mole of the bonds of a particular type between the two atoms in a gaseous state. So in a gaseous state, to break this OH bond, how much energy is needed per mole? It is called the bond enthalpy. Bond enthalpy is defined is a kilojoule per mole. Okay, that's why they are saying 1 mole. Okay, so if you see, for example, is the hydrogen gas. So to break this hydrogen gas as a hydrogen atom, we need this energy is 435 into 8 kilojoule per mole. So hydrogen bond. So to break this hydrogen bond, we need this bond enthalpy 435.8 kilojoule per mole. Suppose this N2 bond. So N2 means we know that N triple bond A. So to break this N triple bond A, we need this energy. So to break this bond, we need the energy is 946.0 kilojoule per mole. Okay. So if you see, so there is a single bond, there is a triple bond. So to break this single bond, we need this amount 435.8 kilojoule per mole. But to break this triple bond, we need 946 kilojoule per mole. So from that value, we can say that triple bond is more stronger than single bond. So from that bond enthalpy value, also we can know about bond strength. Okay, so this enthalpy value, from that enthalpy value, we can know about the bond strength. Okay, so there are the various type of the bond is there: single bond, double bond, triple bond. Generally, if you see the bond strength order, triple bond is greater than double bond than the single bond. Okay, so to break this triple bond, we need the high energy. To break this double bond, we need the lower energy than the triple bond. And to break the single bond, we need the lower energy than the double bond and the triple bond. So this is the order of the bond strength of the triple bond, double bond, and the single bond. So point is that in the gaseous state, to break the bond, how much amount of the energy is needed? That is called bond enthalpy. Uh, from the bond enthalpy value, you can know about which bond is the most strength. Now there is some point is that another also is point that for that water molecules, the difference is bond enthalpy. The value shows that second which bond undergo the some changes because of the charge, the chemical environment. This is the reasons for the sum they different. So what is that? For example, this water molecule. So what is saying that for the water molecules, these two bond is not the similar. Two bond is not the similar. Okay, how you can say these two bond is not similar? You see, if you first break this bond, okay, if I the first break that bond, then that will be formed and that will be. Okay, so to break this bond, we need the energy is 502 kilojoule per mole. So now again another bond is that one. So to break this bond, the amount energy, so required energy is 427 kilojoule per mole. So if you see that two value, huh, there is a huge change. So first of all, for that water molecules, there are the two OH bond is there, but we are claiming that these two OH bond are not similar from that bond enthalpy value. First, whatever OH bond is broken is there. For that, we need the 502 kilojoule per mole. But for that second OH bond, we needing it is 427 kilojoule per mole. So from that bond enthalpy value, we can easily say that two OH bonds are not similar; they are the different. Now the why question is that why? Because if you see for that water molecules, uh, this oxygen, whatever electron density is there, this electronic environment for that oxygen and for that oxygen, these two oxygens will have the different electronic environment. So due to the presence of the different electronic environment, this bond strength of that which bond will be the different. That's why the two different value of the energy are the needed to break that two different OH bond. Okay, so So this is an example. Uh, this is an example of for that water molecule. So similarly, if you see there are the lots of polyatomic molecules. Polyatomic molecules. So for that polyatomic molecules, you have to write the mean or the average bond enthalpy. Mean or the average bond enthalpy. So what is the means of that mean and the average bond enthalpy? Because once we are talking about the polyatomic molecules, so there are the lots of bonds there. Okay, so there are the lots of bonds. So whatever bond is there, we do not need any that, but you have to know the total amount of the bond. So total amount of the bond enthalpy. Suppose for that polyatomic molecule, suppose there is the two bond. There is a suppose the two bond. Okay, so for that two bond, we need for that first bond we need suppose for that water molecule. Okay, first bond. So to break this first bond, we need the energy 402 kilojoule per mole. And for that second molecule, for that second OH bond, we need 427 kilojoule per mole. So there is a different value. So these are the different value for that bond enthalpy. So we cannot say the bond enthalpy of that water molecule is 502 kilojoule per mole and the 427 kilojoule per mole, because these two value are the different. So for that situation, you have to use the mean or average bond enthalpy. You have to use the mean and the average bond enthalpy. So for water molecules, the mean or average bond enthalpy equal to 502 plus 427 by 2. So it will be 464.5 kilojoule per mole. So the mean and the bond in the mean or the average bond enthalpy for that water molecule is 464.5 kilojoule per mole. So for the polyatomic molecules, we have to always use the average bond enthalpy. Otherwise, it is a two atomic molecule. There is the two atoms are the same like the H2, N2, O2, Cl2. Then you have to use the bond enthalpy. Simply the bond enthalpy. Now, another bond parameter is the bond order. So, what is the bond order? Bond order is nothing. It is a number of bonds. In the Lewis descriptions of the covalent bond, the bond order is given by the number of bonds between the two atoms in a molecule. So it is a description. It is given by the number of bonds between two atoms in a molecule. In a molecules, there is the two atoms. So suppose this is a one atom, this is a another atom. So for that case, bond order is equal to 1. For that case, bond order 2. For that bond order 3. Because if you see that between these two atoms, one bond is there. Between these two atoms, two bond is there. Between these two atoms, three bond is there. So number of bond equal to the bond order. Like the N2, bond order is 3. Like the carbonyl, bond order is 3. Like the F2, bond order is 1. Oxygen, bond order is 2. Now there is some point is that isoelectronic molecules and the ions will have the identical bond order. This is the point. Isoelectronic molecules or ions will have same bond order. Like you see that F2 and O2 minus. For that molecules, whatever electron is there, O2 minus will have also the same electron. So the bond order is equal to 1 because FF bond is there. Similarly, if you see the C triple bond O, N triple bond O, NO, and for this N triple bond N, these are also isoelectronic. So the bond order equal to 3. Okay. So for that isoelectronic molecules and ions will have the same bond order. Otherwise, the bond order is the number of the bonds between these two atoms which are the involved to make a molecule. So there is another some points from that bond order value, you can know about, suppose when you see the bond order is increasing, so bond order is increasing, that means bond strength is increasing. Bond strength is increasing. So bond strength is increasing, that means bond length is decreasing. If you compare that, this is the FF bond order is 1, but that for the N2, NO and the CO, the bond order is 3. So these bonds are the strength, these bonds are the more stronger. The bond strength of that CO and the NO is the more stronger than the F2 and CO. But when the bond strength is increasing, then the bond length will be decreasing. That is the case. Another thing we will know about the resonance structures. Resonance structure, so it is often observed that a single Lewis structure is inadequate for that representations of a molecule in conformity with its experimentally determined parameters. Okay, so resonance structures, there is that point is that, suppose the O3, ozone. If you draw that ozone, this is a Lewis structure. So for that Lewis structure, if you ask for the drawing of the another resonating structure of the O3, so another will be like that. Okay, so this is one resonating structure, this is another resonating structure, but both resonating structures are equal like that. This is called resonance hybrid, and these are called resonance structures. Resonance structures, or we can also say that canonical form, and these are called resonance hybrid. So this is called the resonance hybrid and this is called the canonical form. So ozones will have the two canonical form. Another one is the 1, another is the 2. But these two canonical forms are equal to this resonance hybrid. Now the question is that if you see the theoretically, this is the theoretically, this value is that this value, this ozone bond length is 148 and this bond length is 121 ppm. Similarly, that one is 121 ppm, this is the 148. But if you experimentally, if you see that this bond length is 128 ppm. What is like that? Because for that canonical form, if you see that this resonance structures, this bond is purely, we are saying this bond is pure double bond. This is a pure double bond, this is a pure double bond, and this is a pure single bond. But for that resonance hybrid, if you see, these are not the pure double bond, these are not the pure single bond. This is the partial, if you see, is a partial double bond. You can see it is a partial double bond. So this, so this is the double bond, and this is called the partial double bond. So there is also the double bond characters is there, but it is not the fully double bond character. This is a fully double bond character. This is not a fully double bond character. So when it is a fully double bond character, then the bond length will be the less than the partial double bond. That's why if you see that this bond length is 121 and for that partial case bond length is 128. That is the case. So ozones, if you see that ozones has the two things. One is the resonance structure, another is the resonance hybrid or the canonical forms or the resonance hybrid. So according to the concept of the resonance, whenever a single Lewis structure cannot describe a molecule accurately, a number of the structures with this similar energy and the positions of the nuclei, the bonding and the non-bonding pair of a resonant electrons are taken as a canonical structure of the hybrid which they describe the molecule accurately. What is mean of that line? If I draw the again for that ozone case, the two resonance structures is that ones. First point is that for the two resonance structures will have the same energy. Energy will be the same. If you draw this energy profile diagram, okay, these two energy will be the same of the two canonical forms. position of the atom also will be same. Position of the atoms also will be the same, but position of non-bonded electron, or we can say lone pair, will be changed. How? If you see, there is three lone pair. There is one lone pair. There is the two lone pair. Okay. So to draw this canonical form, to draw this another canonical form, you have to move this lone pair like that. So now this lone pair is here. So actually this lone pair is coming here. So here now the two lone pair. Now here there is the three lone pair, but here if you see is the two lone pair. So actually the lone pair or the bonded electrons, lone pair or the bonded electrons also, the positions will be the change. Okay, if you see this bonded electrons is going there and this lone pair actually going here. So the position of the lone pair and also the bonded electrons will be the change, but the nuclear, the position of the nuclei will be not the same. Will be always the same. The energy also another point is the same energy. All the chemical forms will have the same energy. So this is the points of the resonance. And also we will know about the resonance in details in the class 12, I think. So here I will stop the lectures. So basically here I have described here the bond enthalpy, bond energy, lattice enthalpy, bond orders, resonance, and the bond angle also is there. So here I will stop and thank you very much for listening.